So good evening, ladies and gentlemen, dear colleagues, dear guests. Today's scientific evening, we have a lecturer from the National Institute of Chemistry from Ljubljana, Associated Professor Nejc Hodnik. And I will give you a short introduction on his CV. So, Professor Hodnik graduated and also received his PhD degree at the Faculty for Chemistry and Chemical Engineering at the University of Ljubljana. And as a young researcher, he worked at the National Institute of Chemistry at the Department of Catalysis and Chemical Engineering with Dr. Stanko Hočevar, who was that time the leader of the fuel cells at our institute. So in 2014, Professor Hodnik received an individual Marie Curie fellowship and went to Germany, to Düsseldorf, and worked with Professor Karl Meinhofer. After that, he returned to the National Institute of Chemistry in Slovenia, and he received also a postdoctoral project from Slovenian Research Agency and 3-month scholarship that he could go to one laboratory in Italy with ERC grant. So then he applied for the first time for ERC starting grant, and he didn't get it, but actually he got complimentary fellowship from the Slovenian Research Agency. And the next year, that was last year, he finally got ERC starting grant. And this year, he will build his own laboratory for electrocatalysis at the Department of Materials Chemistry at our institute. And actually, he will do, like you see here, his own approach to electrocatalysis research. Because when we hear this word, electrocatalysis, we are thinking about fuel cells, electrolyzers, and such similar devices. But actually, electrocatalysis is much more of this. And now I would like to invite Professor Hodnik that he will show us what is this, more on this. And I forgot to tell you that also last year he became an associated professor at the University of Nova Gorica in the doctoral program materials. And I am very happy because we have now also the topic of electrocatalysis in our program. So, Nejc, please, the floor is yours.
Thank you very much, Natasha, for your kind words. Thank you for inviting me here to give a kind of a lecture overview of the topics that we do. Let me just start. I prepared this talk more to introduce to you what we do, but also to introduce to you the topic of electrocatalysis. So here is a picture of our institute, and here is this new Prigel Center. And then we have a swimming pool in the background for a nice scenery. To show, of course, you know where we are, but still, I think we are quite nicely situated in the kind of the center of Europe, and then we are quite close to a lot of interesting cities and interesting collaborators. And I think this also gives us, it's a good place to do science, Slovenia. Now, the city of Ljubljana I also want to promote. It's very nice, and our institute is actually in the city. It's one of the advantages of working also in our institute. Here is the picture, so the first picture of our group. We call ourselves ElectroCat, Electrocatalysis Group. We have these t-shirts, And I'm now leading this group. I'm in the department of Miran Gabršček, Professor Miran Gabršček, so in the department of materials chemistry. So we are kind of covering more topics, which are all centered around synthesis. So this department is anyway, main thing was the synthesis. And when we bring electrocatalysis, they already have a strong microscopy group. We are collaborating then with other departments from the institute, so analytical department, so my previous department of heterogeneous catalysis and engineering, and we are also dealing with recycling now, and of course we have to simulate process to really understand it. Here again is the topics and the people. So we are quite a strong group now, which is like ERC is a part of this laboratory. But we cover all these things, and in the institute, so we have this, I'd say, unique capabilities under one roof, where we circle around these three: microscopy, characterization, and synthesis. So this is mainly electrochemistry, but then we have people to help us inside the institute to do the engineering, the theoretical background, and then also, of course, neighboring institutes. Now this is a slide I actually got from my colleague, because we have this, our only Nobel Prize winner in chemistry, I mean, in general, and his own contribution was in like an analysis, so microanalysis, organic, and in this spirit we also try to build our approach and our labs. This is the Pregel Center, so now we are making our laboratories in the ground floor, so behind this, in the second rooms, behind these rooms, and we will have the synthesis part, and then in the basement we have the TM. So this is how it looks. And in this Pregel Center, we have a lot of analytical equipment. It spans to almost 20 million, if we count also the NMR. So I think this is the basis for really good work. So this is some of the machinery that we use. I will not go to details, but this is the spirit. So we have good tools, we can do good science. Now I will go to the one part which I always emphasize in my talks, and this is the problem that motivates our work. Of course, one of the things, and this is my personal view, is the global warming. Some people don't agree with this, but still I will try to give you what I think. So this is the killing curve. Actually, it's the measure of CO2 in the air. So what we see here, that if you go really back to history, the concentration of CO2 was quite constant. Of course, if we go further in history, it was also higher when the dinosaurs were there, but this was quite constant. And now, since the Industrial Revolution, this went up. And now we have around 415. Before it was about 200. So this coincides with the consumption of the fossil fuels, and if you see, this is practically the same year. It also coincides with the amount of people that grow, so we're consuming a lot of energy. Now, of course, you have all these record-breaking years. Every year was the warmest, every month now is the warmest. I will not go to these details, but if you don't believe in the global warming, maybe the pollution is something that could bother you. So you have these conditions in the cities that you know, for instance, in China, they really push now to make cities more electric, so to have electric cars. So usually we do things when it's too late, so when we are too sick. But this is then the motivation, and then I really like this slide from the Richard Smiley, where he explained what is the 10 top problems of the humanities for the next 50 years. So he he collected these 10 problems by asking the audience, and he got something like this. So, and then this was not the first order how they are by the importance, but he made then a mental experiment where he said, which of the issues, the problems I can solve, and then this problem solves all the other problems. Is there such a problem? And of course, he identified the energy. And this is what's interesting. So, of course, the energy problem is correlated with the CO2, and we are consuming more and more. So, is there a way to get clean energy? So, if we would have abundant clean energy, we could, in principle, solve the problem of water. Because there's a lot of water around the world, we could just take the seawater, clean it with, of course you need power to separate salt and water, so you need energy. So we can actually get rid of the second one. So then the third one is the food. This, you must have water to put to the food to grow and then to feed the animals. And of course you need the ammonia, which you get by Haber-Bosch, where we consume a lot of energy to produce the ammonia. And then, if you go down the line, you can see that the energy is really the #1 issue that could actually be solved. So, this means that this is the motivation and this is the target that we need to solve. Of course, the other thing that would solve all these problems so we are in the trajectory to be 10 billion. So if we go to 1 billion again, this would also solve the problem, because then we would not consume so much energy. But I think this is not realistic. In nature, the energy circle, as we know it, so it's this carbon circle. It's storing the energy from the sun. Which is very abundant. But it's too slow for this amount of people that we have. So it doesn't work. It doesn't consume the CO2 from the air. So we need to increase it. There's also one other circle, which is nitrogen circle, which we found a way with this Haber-Bosch process to make ammonia from the nitrogen from the air, and this can then be used as a fertilizer. But in nature, this is too slow. Now, this is an interesting slide. It seems that we are just complaining about what we did wrong, and like the older person would then come and say, you know, stop complaining about what my generation did wrong and try to find a solution. So what could be the solution? So from the past we can learn that, again, you had this Haber-Bosch, and at that point there was no ammonia. So they need to make fertilizers. So they give the scientists the task to find a solution. And of course, he found a solution. He made this high pressure, high temperature reactor to combine the nitrogen and hydrogen and then get the ammonia out. So this is the nitrogen cycle. So the scientists find the solution. Then you have this, Germany, they needed to fuel the tanks with the gasoline. They had embargo because of the war, so there was a challenge. So they make a partial carbon cycle, I call it. So they make synthetic fuel out of the coal, and of course high pressure with hydrogen. You do it, and again you get the Nobel Prize. In addition, also this Fischer-Tropsch process was kind of similar high pressure, so it's a catalytic process. So if we go now to the present, we must find ways to store the solar energy. That's the only sustainable solution that we know. And this will then, we will then be, because all this hydrogen that I mentioned before came from fossil fuels. It's reformed hydrogen. So, we must find a way how to do this without this. So we need to take the energy from the sun which is, as you see, very abundant. In less than an hour, there's enough sun energy shines on Earth to cover the humanity for a year. There's this one graph of how much land we would need to cover to get enough energy for all humanity. So in theory it's doable, but then we have problems because the sun is not shining at night. So we need to store this energy. So how to store it, how to convert this energy into some chemical energy. You can do this by converting biomass or CO2 back to fuels, but here I introduce this hydrogen economy concept, which is, let's say you have wind, and wind is also sun energy. So you get electricity, you use electrolyzer, as was mentioned, you make hydrogen, so you split water with electricity, so with energy. You store hydrogen, and when you need electricity back, you use the fuel cell to extract electrons from the hydrogen back. So again, you have hydrogen here as an energy carrier, but you got it without any carbon, just by splitting water. And then you could run a home like this without off the grid, ideally. Now, how this reactor looks like, so you would have a fuel cell. This is a fuel cell, proton exchange membrane fuel cell. You put it in a car, and this produces electricity, then an electric motor runs the car. But if we zoom in inside and look how this looks, so you have anode and a cathode, which is split by the membrane. It's the easiest if, and then you have a catalyst which looks nanoparticles on high surface area carbon. And this could be like a model system. So this is, I'm showing you this picture because I will talk about this a lot later. So it's metallic nanoparticles on carbon support. But back to fuel cell, this is how it works. So hydrogen comes, gives electron to the wire, and give proton travel through the membrane, and then recombine with water, with oxygen, and form water. This potential difference of these two reactions gives the voltage and gives the current. So this is how we get the current out. Now the other reaction is the proton exchange membrane electrolyzer is just the opposite. So you push current to split water. Here you split water to protons. You make oxygen, and these protons go on the other side where they recombine with electrons and become hydrogen. So it's just the opposite reaction. Here you push the electricity, and the other way you drain the electricity out. So the catalyst. In this case, to split water to oxygen, you need iridium or ruthenium. So like platinum, it's very expensive and rare. But on the other side, so you should have platinum to make this hydrogen evolution, but you can also use something else. You can use copper, and then you can electro-reduce CO2 back to fuels. So this is using copper, and then ideally you could also reduce the nitrogen back to ammonia, and for this the only known catalyst that shows some activity is nitrogenesis, which is an enzyme. But it's still super low efficiencies, but there is something there. Now a question, what is a catalyst? This is just like a general slide. I will be maybe fast. So catalyst is a substance that increases the reaction without being consumed in it. And a good catalyst makes the process more efficient. So if we look at the thermodynamics, we need to come from here to here, and a good catalyst means that the barrier that you need to cross is lower. And then you have these two carbon cycle and water cycle reactions. It's then the reactions are there. Now here's I was thinking about this, how to explain this, and then I realized I even don't know exactly. So what's the difference between catalysis and electrocatalysis? And what is electrocatalysis? It's actually an old field. It's actually happening just on an interface, like in catalysis, but here you have a metal electrolyte interface, which is liquid electrolyte. And in electrocatalysis, you always have reaction decoupled. So you have oxidation, and then you have a reduction reaction. So these are split into two parts, like here. So you split the reaction. If you would have catalysis, this would be just, at one point, you would just make this bang. It would explode, I mean, it would make a loud noise. So, and if you look at the surface, in catalysis you have some molecule coming to the surface, it absorbs, reacts, and then it dissolves. This is quickly said. But in electrocatalysis you have the electrolyte. So it means water, and you have this electric, this double layer. In this double layer there are anions and cations, and there's electric field. So there's drop in electric field. So there's a lot of interaction between cations and anions and water with the reactant. So it's a lot more complex. And actually just by studying this double layer, it's already very, very challenging. Now, of course, then this is the where it happens, these two reactions. Here is also one general slide. What is a nanoparticle? Maybe I will not spend too much time here, but it's something in the nano dimensions. The important thing is that the properties change. They are not similar as the bulk surfaces, but most likely you gain a lot of surface area, which is good for catalysis. I think just for imagination, it's good to know the 2 nanometer nanoparticle has 300 atoms, and 300 to 5,000, and 4 nanometer has 20,000 atoms. So we're quickly going to a big number of atoms, and they're used as electrocatalysts. Now, if you just look at the shape of the nanoparticles, and if you look at Platonic shape, Plato, they were defined as the elements of like earth, water, fire, and air, and something which is not doesn't exist. But the problem here is that also we are looking at nanoparticles something, you know, ideal. And this was the first image I was taking as my ERC because I'm studying nanoparticles. But when you look at the nanoparticle in the microscope, like in this study, you can see that they are far from perfect. So they are not these perfect shapes. So here they compare this magic number cubo-octahedrals with the same amount of atoms as the real nanoparticles that we see in the microscope. And if we count how many defects they have in coordination of the surface atoms, so you compare here, so this is perfect particles and this is real particles, you can see there's a lot more defects. So coordination number is how much atoms are around one atom. So you choose one atom on the surface and you count how many neighbors it has. If it's perfect, you have a lot of atoms. If it's very defective, you have not so much atoms. So the coordination number is low. And this is very important because it affects how we actually see the catalysis and how we do maybe theoretical work. So this is when I changed my kind of image for my grant to this defective surface. And the important thing is that no two nanoparticles are alike. So you cannot you will probably not find the same nanoparticle if you look at the microscope. Now, why this is important? Here is the slide, is just to confuse you, but the point is that you see that there's many effects that influence the catalytic activity of the nanoparticles. So you have nature of the nanoparticles, support, surface area support, morphology, structure, composition, presence of defects, kinks, add atoms, so different morphology, everything. And then you have also alloying effect, confinement effect, proximity, so practically everything. So it's very sensitive, especially in catalysis, especially electrocatalysis, to all these features. And if you think about if you're calculating maybe some DFT calculations, this will change the what you get out if you put a defect or if you don't. And this is then one image how you can tune the catalyst, and the complexity just grows. So I will not take here time, but you're making alloys and then you're putting some ligands and external forces, but this can all tune the activity. Now, the state of the art in electrocatalysis is the structure-activity, also structure-selectivity relationship, and understanding on this on the atomic level. So this is what I also said in my ERC talk, which is good, but what about stability? What about the changes of the surface? Because this is not just like as you choose it, and it's definitely changing. So do we have this structure-stability relationship? And this is where I actually is my approach and where what I'm focused in. And this is where I show this example. So how does surface change of this, or how does this nanoparticles change? So we'll try to cover platinum as a fuel cell catalyst, iridium as electrolyzer catalyst, and copper and silver as a reductive catalyst to make some electrosynthesis. In proton exchange membrane, these curves should just tell you that we are losing activity. So it's not stable, it's certain protocols, we're losing power, we're losing surface area. Depends on which protocol you have. If you cycle to higher potentials, you're losing the surface area much faster. So surface area means activity practically, because if there's less surface area, there's less catalyst to run the reaction. Here is the typical CV. I said I would show one CV, and this is here, cyclic Voltammogram, and it's the only one. So here are the features of platinum, which are getting smaller, so it means you're losing the surface. If we try to understand this, we must first map out the different mechanisms that can occur. So you can lose surface area by dissolving platinum, by corroding the support, and by, of course, dealloying, so removing of second metal, this can be considered as a primary mechanisms, and then these ones below are secondary because they result because of the first one. So you have agglomeration because you maybe corrode some support and particles coalesce. You have osteotripening because you dissolve smaller particles and redeposit on the bigger ones. You detach particles because you probably have carbon corrosion or somehow. And then you can also reshape. So this all influences their structure. Now, then the question is how to distinguish between, let's say, these two mechanisms, because they both result in the bigger particles. So osteotripening, dissolution of small ones to the bigger ones, and this one is coalescence, and then you get big particles. So there's an old way to do it. You do the particle size distribution. You can do this with different techniques, with XRD also. And then if you examine this, and if you see tails to larger particles, you say, okay, so tails, because you have more larger particles, you can say, okay, this is coalescence or agglomeration. But if you have tails to the smaller particles, it should be ostwald ripening. Now, this is maybe good if just one mechanism is happening and you don't have any information what's happening with individual particles. So it's quite broad and general. Now, what I propose and what we do is we say, okay, we will care just what happens to one particle, and we will play a game. And this game is, you should find the difference in these two pictures. And this picture is the same location. So it means it's the same picture, and you have to find differences, like in a children's game. So we say, okay, if we map the same particle before some degradation and after, and we see there's some atom column missing, we say this must be dissolution. If there's some particle missing there, we say it obviously detached or moved. If you see a hole in carbon, it's corroded, and then we see new particle. So in this case, we are certain that this event happened because we know the history. And this is something which is important because in other random microscopy, you never are sure if this particle was already like this or not. And you don't know what happened to this particle. You can have statistical knowledge But if you really look at it, you can really say, okay, this is what happened. Now, how you do this in reality is you take these TM grids, which have numbers inside. They are called finder grids. Because they're gold, they can be used as an electrodes. So you take the first image, you put it, then the grid in the electrochemical cell, you do the treatment, and then you find the same location. So it's pretty straightforward, but it's a lot of work. So this is how you track the same location. There's O, we zoom into O, and then you find this catalyst, this part. So this is nanoparticle, this is SEM. Now and then if we look at one typical event, we can see that there's much more mechanisms happening at the same time. It's not just one. So you have the attachment, dissolution, carbon corrosion, and agglomeration on just, practically one picture. So it's a mess. So it's really impossible to do it unless we really observe the same location. Now I want to introduce you this dealloying, which is selective leaching of the second metal, because usually we use platinum alloyed with something else as a good catalyst, but this second metal is copper or nickel or cobalt, which is not stable in acidic media, so it's dissolving. And particularly it's interesting when it's dealloying, it's because it leaves behind a porous structure. So this happens when you have a high composition of the less noble metal, so it should be high enough, so there's a critical composition. And if you pass a critical potential where you push it out, so you oxidize it out. So this is the mechanism. What's also interesting here, because this mechanism is working in a sense, you have surface diffusion of platinum, which is protecting copper inside, and then at a certain point when you raise the potential enough, the copper is forced to go out. And I'm telling you this here because if you have nanoparticles and then you go to the smaller dimensions, it seems that the surface movement of the surface atoms is higher. So this is kind of Gibbs-Thompson effect. So it means if you're smaller the particles, diffusion will be higher. This will come later here. And this means that smaller the particle, the less chances is that it will become porous, because this platinum is faster on the surface and it's like healing the surface. And if it's bigger, it's slower, then the copper has time to escape. And this was nicely shown here. Of course, we did also tomography on the same location, but you see the bigger particles, they make pores, and the smaller ones, they stay the same. And the porous one also shrink because you're losing 50 to 75% of copper, depends on the particle size. Now here's more images. Now we show a lot of images. So what we see here is again porosity. What's interesting here, if you do the degradation more, so you expose these potentials, you actually see the porosity coarsening, so the pores grows. So it means when you make pores, it's not the end of the story, they also change. So they grow, and this is then the mechanism where you lose surface area. So the surface area of this one is higher than this one. This was interesting because we did this study when I was in Germany. We have platinum nickel, nickel goes out, but when you continue to cycle, you can see that the pores kind of grow and they tend, in the end, should make a smaller surface. And this is happening at relatively mild conditions, which I think it's really important. And because this is happening because the surface is actually touching each other, and then the surface diffusion can occur. So to minimize the energy. Now, the second effect, which I think it's really interesting, is when you cycle. So not just hold the potential, when you cycle, of course you see the same effect, shrinking pores, but you also see this shaping. And this shaping is something which we didn't know at the time what it was, and it was quite peculiar. And we also didn't know what shape it was going into. After I came back to Slovenia, and we start collaborating with engineers that also do modeling. So in this particular case, it was Monte Carlo, microkinetics. Because we have the same particle before and after, we can kind of replicate what in the model, and we know what we should get. So in this case, the Andras Pavlicic, he modeled this, so he gets this. So and this is how he then tuned the parameters of the Monte Carlo simulations. And what was interesting here is that when we apply a little bit gold on the surface, which has much faster surface diffusion compared to platinum, you see that you don't make pores. So, and how we model this is that we put more monolayers of platinum on the surface. So if you run this model, you don't get pores, you just shape it. Yeah? But if you have just one monolayer, you get pores. And this is again shown here. And this is when we kind of make these images look like TM images, and this is then the real TM images. So the amount of surface monolayers of platinum can affect if you get the dealloying or not, so pores. Then of course, because we have this nice microscope, we should ask ourselves what's happening on the atomic level. Of course, we just repeated the experiment, did a mild treatment to in this resolution you don't see any difference, but if you zoom in you can see something is starting to happen. It's familiar with the shaping. And if you look even closer, you see the atoms, and you see that if you recognize the facets, because you can do it, because you see the atoms, you can see that the 111 facet is getting smaller. And this is peculiar because 111 facet is the facet with the highest coordination number on the surface, so it means should be the most stable one. So why is it then the least stable? And it's also very important because it's usually the most active facet on the catalyst, at least for fuel cell oxygen reduction reaction. And in this case, what we figured out is that if you overlay these two images, you can see that actually these facets are getting removed, so neighboring facets. And just like kind of sharpening a pencil, you're shrinking the 111 facet. So 111 facet is actually the most stable one, but it's these weak facets that are shrinking it. So it's kind of obvious now, but it was not in the beginning. So again, Andras took these snapshots and make the simulation, and then because he made the Monte Carlo, he has the positions of all the atoms. He can also make these nice 3D movies. But what we figured out is that he could only get this etching from the sides if he puts more copper on the sides. So we could only simulate this process if we put more copper on these facets. So this was kind of a backward information. Okay, these facets are more rich in copper, and 111 facet is richer in platinum. You can also make this surface model to see the pore formations, but what's I think very interesting is this geometric phase analysis. So this is just the positions of atoms, and if there's some straining, so changing in the positions of atoms, you just see it as a color. So you're comparing the distance to different atom, and then if distance changes, you change the color of the atom. So it's called geometric phase analysis. Why this is interesting? Because the distance between these atoms in platinum has a big effect on the activity. It's called strain effect. And this is how we actually, the whole community is tuning the activity. So this is why we put copper under platinum. Copper is smaller, it strains the platinum together, and this then gives appropriate absorption energy for the reaction. This is to make it super simple, but as I said, in electrocatalysis, it's probably not the simplest way, because I think my personal opinion is that you affect the double layer, so the interaction with water and the anions, and when this interaction is kind of not as severe, then you give place for the reactions to occur. It's like, but we can talk about it. So in my ERC, I propose to of course, develop these techniques and observe these atoms and to see what's happening. Try to understand it with simulations, and then try to prevent. So what do you do to prevent this dissolution from the sides? I propose to decorate it or to dope it with, let's say, gold or ruthenium or something which is more stable, or maybe make catalyst that doesn't have these facets. It only has 111, but there will always be some other facets or defects, so but you must protect it somehow. But the point is that we build this from the one particle up, so bottom-up approach. We do many studies on different particles, we learn their behavior, and then we can plan new catalysts, which is super stable. Now, just for fun, you can also do this identical location with the SEM. And I think you can also do it with any microscope. So here is just, it's super simple. So you take like a graphite pencil, graphite rod, you make a cross because this will help you find the spot afterwards. And then we have this cleaning procedure for the catalyst. But you can also do EDX, of course, if you have it in the SEM. But this was done 2012 with our SEM, which is kind of good, but you already see all these effects. So you see porosity, you see shrinkage, and you see the shaping on platinum copper. And here is a lot of images which will show you how you recognize the same place. So this is kind of this graphite surface with a catalyst. So this lighter part is a catalyst which was pushed in. So it's a mess. How do you find the same place? Yeah? But I look at it as a map. It's like if you look at the Earth, you can always find Italy. Yeah? So here, if I go back, it's here. Huh? It's like Cyprus or Crete. Then you just zoom in, you have this path, and then in the end, yeah, it's kind of high resolution SEM, but you see it. And then you just take consecutive images, and you just do this cycling degradation. Yeah. Here something strange is happening because you see that the platinum is getting more and more, which is not logical. Yeah. And it seems to work for everything, and what we figured out in the end, that actually platinum from inside the layer is coming out. So it's dissolving and redepositing back on the surface. Here it's just more images. It's kind of 3D post-weld ripening. And if you would do TEM, you would not see this 3D through layer. Here's some FIP. You see more signal of platinum on the surface. What is interesting that if you cut a fuel cell, and this is the membrane and the catalyst and the anode and a cathode, and then this is the degraded one, you can see that in the membrane you have this line of platinum which is dissolving and coming to a certain point in the membrane, which is then getting reduced because of the hydrogen crossover. But it's kind of similar what we saw in our experiment. You can do degradation with higher temperatures. I will not lose time here, but what you basically see is a lot of agglomeration and coalescence because of the carbon corrosion. Now there is one technique I also need to mention, is also was kind of developed, of course, through the idea that we saw somewhere else, but it was developed with the new cell and new kind of coupling. So what you do, you use ICP-MS, or electrically coupled plasma, coupled to MS. So this is very sensitive technique. And in this case, we want to measure online dissolution. So what you do, you have your electrochemical cell, which is kind of complex here, but don't worry. So you have electrochemical cell, you pump the electrolyte in the ICP-MS directly. And because it's so sensitive, and because this electrochemical cell is small volume, you can actually track the online dissolution of platinum. So here is the cyclic Voltammogram and the dissolution profile. So we start here, this is the typical image, and you go up with the potential. So this is the CV, and this is the dissolution curve. So you go up, you oxidize the platinum, and then you go back and you reduce the platinum. This is the reduction peak, and this is the dissolution. So what's interesting here is that platinum is dissolving when you're reducing it, which is counterintuitive. So it's really nicely seen because of this setup. So you oxidize the platinum, here you go to some oxygen evolution. So then you go negative, and when you reduce, you dissolve platinum. It's called transient dissolution. And yeah, it's kind of oxidation, so you make oxide, and then when you reduce this oxide, it seems that the surface is so roughened that when you pull the oxygen out, these dangling atoms, they stay kind of more prone to dissolve because they're not coordinated as much as the others. So now if we go to the proton exchange membrane electrolyzer where we have iridium, iridium is the only good catalyst, and then you have on the other side these others, copper and... So I will show here faster examples. So here we did a study where we compared iridium and iridium oxide, rutile oxide and iridium metallic particles. Iridium metallic is much more active, so if you go to high potentials, you split water much better on pure iridium than iridium oxide. Now if we look schematically what happens, iridium metallic makes a lot of oxygen at these potentials, but it's also dissolving. So the degradation of this catalyst is dissolution. And then if you make amorphous oxide by oxidation electrochemically, you make more oxygen, so it becomes more active and more stable. And if you have rutile structure, it's kind of not active. And this is how the catalysts look, it's just amorphous. I mean, it's just a powder of iridium, kind of, you have everything aside from nanoparticles to different facets, pores, so it's a mess. But this is the catalyst that they use in industry, because it's the only thing that is stable at these high potentials. Now here is identical location, and this is the only kind of one of the rare locations that we saw some effect. So if you look at these extra nanoparticles that are on these surfaces, you can see that they change. And this is the change that occurs. And what's happening here, we say that iridium is oxidizing, and then we're reducing it. It's actually kind of dissolving and falling apart like platinum. And if we make higher contrast, we can see that there's a lot of single atoms forming. So it's actually dissolving by creating these single atoms. And if you lose this oxide, there's no change. So we did this in SCM. But iridium has a lot still to do. This was just some initial studies that were also coupled with other techniques. For ruthenium, that some people say is a good catalyst, I say it's not stable. And if you cycle, you can see the activity drop immediately. For the metallic and for the rutile, it's also dropping. So this is before cycling, first cycle, second cycle. Before, and then 10th cycle, you can see everything is dissolved. This is again, first cycle, second cycle. And for the ruthenium oxide, there's not much change, but something is happening which is decreasing the activity. So we need to study this further. Now, I don't know how much time I have. So maybe I will just do this one fast. So this was all degradation at higher potentials. So now, what's happening in the negative potentials when you go to the hydrogen side, to the other side? And here you can see that this identical location, you can see coalescence. So it's coalescing, is this mechanism. Here we made vertically graphene fences, and then we prevent the movement. So what we see, so we nicely embed particles. I will just skip, but we can see if we make this graphene, we actually prevent the loss of activity. So this is without graphene and with graphene. So if you know the degradation mechanism, you can prevent it. There's some nice, interesting phenomena that's occurring in the negative potentials. You have to go to the kind of -10 or more, and then you get this. You're making smaller particles from the wire, so you can see the surface area grows from here to here. It's called cathodic corrosion. So the idea was, if we degrade it by coalescence, maybe we can reactivate it by this corrosion. And I think, yeah, we were the first one to show actually this. So it coalesces, and then you reactivate it by this cathodic corrosion. So you actually go to -2 volts to degrade it, and then you go to -8 volts to reactivate it. Maybe, yeah, this is then a slide which we just prepared for some paper, but it's degradation of copper and copper mechanisms for CO2 reduction. And it goes from post-ripening fragmentation, which is a completely new mechanism, so in negative potentials, this is kind of cathodic corrosion. Then you have poisoning on the surface, the attachment. So we are trying to take what we learned from platinum to iridium and now to copper. And I will finish here, and I want to thank all the funding agencies and of course you for your attention.
Thank you very much for a very interesting lecture. So now the lecture is open for discussion. So there are any questions? No? Okay.
Thank you very much for the very interesting lecture. It was really very interesting, different kind of topics you covered. I was wondering, I'm not so familiar with fuel cells, about iridium, ruthenium, this mix, this kind of catalyst. What is the usually the pH in this kind of, the pH?
Yeah, the pH is very acidic. So these are proton exchange membrane electrolyzers or fuel cells have a really, really low pH.
Low pH, yeah.
So it's 0 and lower.
Commercially usually sold mixed oxide, ruthenium, iridium oxide. How do you think the combination of the two is not better than single one, or?
It's better, it shows higher activity. I think this is one of the ways to improve there are two ways. So you can have iridium oxide, which is not as active. So you need to activate it, so you add iridium. No. Iridium is the iridium, and then iridium oxide, and then you add ruthenium to make it more active. So what you can also say, you add to ruthenium iridium to make it more stable. So iridium is more stable, ruthenium is more active. So by combining these two and oxidizing them, you stabilize them.
Mm-hmm. And so what I understand is that currently there are no that kind of good catalysts which can do this kind of oxidation reaction in acidic environments. Is it some of the challenge?
Yeah. The iridium is actually a good catalyst. The problem is that it's 10 times less than platinum on Earth, and even platinum is super rare. So, and if we want to make this clean energy, so to make hydrogen from water with solar, you would actually need more iridium than platinum. Okay. So the real big challenge would be to replace iridium or to find some new catalyst that works in acidic media. So acidic media is good because the PEM electrolyzer is very useful. It's very small, compact, and it can be turned on and off quite quickly, and it can handle high current densities. Whereas in alkaline media, the current densities are still low because you don't have a good membrane yet. Mm-hmm. Although they are making now membranes, it's still not there. But if you would go to alkaline, you don't need iridium. You can have nickel iron.
Okay, thank you very much.
Thank you. Yeah, Matthias.
Some year ago, there were news on our media about Chemical Institute developed a very cheap and effective catalyst for fuel cells. Have you been a part of it? Do you know anything? What's going on with this now?
You said cheap.
Well, cheaper than today's catalysts.
So it's cheaper because you put copper inside. So if you imagine you have platinum particle and then you put 3 times copper inside, you dilute this, so you actually make it bigger. So the same mass of platinum now gives you more surface.
But did you take this into some kind of further development, in commercialization, whatever?
It is in this initiative. So Kolek, I think he made a company, and now he's pitching to get money. And Stanko Hočevar is also kind of fuel cell developer in his company, Mebius. So, but to get this from out of research to the commercial product it's long time. But
okay, but you are on the way. You are trying to do that. I mean,
no,
people at Chemical Institute. Yeah. Oh,
I'm
inventors.
I'm part of inventors, yeah. But I said I will stay in the institute, so I can be in some advisory board. But for me, the companies are too scary business.
Okay, thank you.
There are some more questions? No? So maybe I have one. I read in your CV and your C grant that actually you would like to also develop the advanced characterization methods for electrocatalysis. So what did you mean? What kind of methods? Not here we saw the microscopy, no? But
yeah. So yeah, microscopy is the one which is the most, I think, for me, the intriguing, the nice one, which is really I think the most original one. But we also developed this online dissolution methods, which gives you then insight into the mechanism of dissolution. And when you change the particles or the surface, you actually see the difference. So this is one, and the other one is that there's a special setup where you increase we call it floating electrode. So if you use pure electrocatalytic way, you dip the electrode in the electrolyte, and then the diffusion of the reactants is problematic. So, and then that's gases. So that's why we were thinking of the method where you put it on the surface of the electrolyte, and then the diffusion is from the gas phase, and then the reaction is happening in the interface. So this would allow us to have to measure high current densities and to do the degradation at high current densities. And then this would all be coupled in one setup. This is kind of idea. And then there's also a setup where you measure with the online MS the production of gaseous products. So if you, let's say, see corrosion of the catalyst, you would see CO2 in the MS. So you're looking what's dissolving and then what's coming out as a gas. So also, interestingly, iridium oxide, I think iridium 04 is a gas. So you could also sense this, I think. For ruthenium, I'm sure, but for iridium. And this could then tell you about the mechanism of degradation and if you change the mechanism or not. So by coupling all these techniques into one device and studying one particle, this will then like a bottom-up knowledge of what's happening, and then maybe idea how to fix the problem.
So maybe I don't know if you have more questions. Maybe you will be more brave with the glass of wine on the ground floor. But still at the end, I would like to ask the last question. So what would be your advice to apply for your SEG grant if somebody maybe has an idea? So because actually for the first time you didn't manage, so probably you have some experiences why, and now you know how you can win. So maybe.
Yeah, it's for me, I mean, of course, you have to have a good enough CV, which kind of you see who got it, and then you compare, and you see that you can also get it if you're not, you know, crazy sighted. But so good CV, and the idea, you should feel that it's good, but this is not enough. You should be lucky to get through the first round, and then you're 50-50. But my first problem was I prepared a project which was, how they put it, medium risk, high gain. So no, they found high risk, high gain. So that's why I promised I would make super stable catalyst.
Okay.
So before I didn't promise that I will make the best thing, I just promised that how I will do it, and then I will see what I do.
Okay.
So it should be high risk again, and then it should be original and your idea.
So did you do everything by yourself, or you have some help from some companies or European office at our institute?
Yeah, I mean the office helped a lot, just to arrange all these documents. First year I had one company to help me write and to challenge my, what do you really want to do? What is the breakthrough? I had the Skype, and it was good, but in the end in the end you have to do it. So the next year I didn't need it. I just, because in the end in the commission you have, in this board panel, you have scientists. So they really want to see the science behind. So it's, of course you need to have a nice concept, but then they really need to see that, okay, you know, it's kind of, I talked with one guy, he said, you know, just imagine, would you hire this guy to do this job in your lab if you had like a department? So and then it depends who's in the panel, and it's...
So maybe it's a little bit different as European project, because now for European projects, actually a lot of people just hire the companies and...
No, this is they really look if you are the guy to do this. So it's obvious if you just look through the papers and you see, okay, you know, he was not doing this, why is he proposing this? So it's the really panel is really taking time to study if you are the person that is capable of carrying this on. So it's if you put something generic, it will not go through. There should be some logical way why you are suggesting this. You know, it's you cannot just suggest something that you didn't do before. So there should be some background and some uniqueness that why are you the only one that can do this interesting thing that you do, that you propose. And but it can happen. I mean, it happened to me. So I never thought it would, but it did. But then you see that it's just you're pushed in this, and then you have to focus, and then after 1 year it comes out. If you put a lot of effort, something good will come out anyway. You know, it's kind of.
So your advice will be that we have to think about such a project, or not?
No, yeah. I mean, it's I think in Slovenia it's sometimes hard how to get independence from the mentor and how to show your own path. But if you go out, so one guy said to me, if you go out, you have Marie Curie, you show that you are capable, you have then article with somebody that's not your mentor, and then it's checked, it's okay. But I think we should think about younger people that they should have an option to apply, you know. So and for this we have to give them freedom to develop their own something. Yeah. So I think you cannot just, okay, now I will apply. I think it takes, I was thinking about this for like 4 years for sure. But somehow I had luck because I was like always, not the main thing at the department, I was kind of the odd guy who's doing something strange. They didn't know what to do with me, so I always had my own work. So this kind of helped me, but at that time I was not happy.
So thank you very much again for your lecture, and thank you very much also for your attention.